So we're going to talk about centripetal motion, circular motion that happens in the vertical plane. Because there are some things about it which are quite unique. And the biggest one is that gravity is going to play a role as a centripetal force. We know that gravity is always pointing straight down. And a centripetal force is one which is pointing towards the center of circular motion when an object is moving in a circle. So what I have here is a marble, and you can sort of visualize what's going to be happening as the marble moves around the circle, or we could just watch. There we go. When the marble is at the bottom, down here, gravity is pointing straight down. So it's lined up with the center of the circle, but it's actually pointing in the opposite direction. And so at this particular moment in time, it's actually the normal force pushing up out of the ramp, which acts as a centripetal force. And that's going to continue to be true as the marble moves around the ramp. When the marble's at either side, the left or the right sides of the ramp, it's pushing into the sides of the ramp because of inertia. Essentially, it's moving forward and running into the side of the ramp, and that normal reaction force of the ramp pushing back, that's acting as a centripetal force. But as the marble moves into the top of the arc, more and more so, gravity is starting to get lined up with the center of the circle. And in fact, when you're right at the top, gravity is a totally centripetal force pointing right towards the center of the circle. And in that case, it's helping the circular motion happen. And if the marble is going fast enough, it's also going to be pushing into the top of the ramp, even up here at the top of the circle. So you might be asking yourself, how high can I drop this, or how low, and still have it complete the full circular motion? This is one of the most important things about the vertical example, is that the speed is going to make a big difference as to what forces are acting on the object. And there's actually a minimum speed that is needed to complete the entire loop-de-loop. The lower down I drop the marble, the weaker and weaker it's going to be pressing into the top of this ramp. And if I find the minimum possible spot, then at the top of the ramp, gravity is going to be the only centripetal force. So if it's too low, it's not going to have enough velocity to make it all the way around. Essentially, gravity is going to pull it away from the circular path too strongly. I'm going to have too much centripetal force. I can never get rid of gravity, so if I don't have enough velocity, then I won't be able to balance out my centripetal force of gravity with the centripetal force equation, mv squared over r. So if I drop it from the top, I've got lots of velocity, which means it can cope with the amount of centripetal force, and it easily makes it all the way around the circle. If I drop it from a lower point, it's not going to build up as much velocity, and gravity is going to pull it away from the circular path, essentially, before it can continue to move, like so. So that's really going to be the key. And if I drop it even higher than the minimum possible point, then again, I'm going to need some extra centripetal force if I keep adding more velocity. So where does that extra centripetal force come from, above and beyond the centripetal force of gravity? That's going to be normal force, an extra reaction force. Essentially, if the marble's moving really fast when it hits the top of the arc here, it's still going to be pressing into the ramp, and the extra centripetal force which is needed comes from normal force.